Hi, I'm Kobe. This is Kirsten, John, Matt, and Kai, and we're on Team Oasis. Oasis stands for the Optimized Auto System for Serious Situations. So a little recap about what our actual project is from the get-go. The Oasis is a water vapor condenser that's intended for disaster and emergency relief specifically. And for our RRP, we focus on a few critical components of our system. The first component is our cooling system. So what actually will bring our system to the dew point of the ambient air around to condense water vapor was one of the things we chose to tackle this quarter. The second was the condensing plate, which is the physical surface area that we're using to condense water and collect it for consumption. And then the third critical component is our atmospheric sensors. And so this is kind of the key for optimizing our system. And so the atmospheric sensors will gather data that tell us relative humidity and ambient air temperature, from which we can then calculate a dew point to then cool our system, cool our condensing plate, and begin condensing water vapor. We also chose for our RRP to focus on Puerto Rico conditions because of the water crisis that's existed in Puerto Rico for the last year since Hurricane Maria. And so that was kind of our target for this quarter. Some of the specs that we chose to attack for our RRP. The first one is that we'll efficiently condense the Seattle equivalent of 2.5 liters of water in 1 day per Puerto Rico conditions. And so in Puerto Rico, we are trying to condense 2.5 liters, but since we're obviously not in Puerto Rico, we need to calculate what the equivalent amount of water that would be per hour conditions in mid-November in Seattle, Washington. The next spec that we chose to meet to this quarter is to cool our condensing plates to below 3 degrees Fahrenheit, 3 degrees Fahrenheit below the dew point. And we want to accurately measure and interpret the ambient air temperature and relative humidity using those sensors so that we can know what our dew point is so we can cool our plates below 3 degrees.
Great, so our risk reduction prototype for this quarter that we built, you can see here in these two figures, this is our overall system setup. We have a 55-gallon drum where the cooling system, condensation plate, the coolers, and our fanned plate is below the coolers to dissipate all the heat from our thermoelectric coolers, is mounted at 45 degrees within the barrel. We have a fan atop the system blowing air across the condensation plate to increase condensation rate overall. Here you can see the condensation slowly building on the thermoelectric coolers as we test. And as we move more into testing, you can see here in figure 4 that water is starting to pool and actually condense on the plate. This was just another view above where you can see into the barrel from above to see the system as it's cooling and condensing water.
And for the atmospheric sensor RRP, we had to read the relative humidity and ambient air temperature using sensors controlled by the microcontroller. And this is just a test that I did in room temperature where you can see the Fahrenheit from the microcontroller, from the sensors, is 75 degrees, and from this meter is 72 degrees Fahrenheit. And the humidity is 49%, where the monitor is 51%.
Great, so our critical design specifications for the mechanical side focused on the cooling plate and condensation rate. We did meet the objective of our cooling plate to cool the plate to 3 degrees below the dew point. We cooled our plate to about 6 degrees below the dew point, so we met that spec. And for our condensation rate, we did not meet the given threshold that we set. However, the spec itself was written poorly to reflect the Seattle equivalent of 2.5 liters in a Puerto Rico environment. So we condensed 0.118 liters over a 24-hour period during our test. However, in future tests, we would then compare it to a Seattle equivalent of 2.5 liters in Puerto Rico conditions. So here you can see the verification. that we got half a cup after running our system for 24 hours. This is just a figure depicting that we did, in fact, get liquid water from the air around it.
And for the specifications for the atmospheric sensor, we did meet our threshold of measuring temperature and humidity within 10% of accuracy. And to be more precise, the humidity sensor was within 3.9% of accuracy, and the temperature sensor was within 4.2% accuracy. And this is just another verification test. This one was set inside of a fridge, just to take the temperature from the humidity and temperature monitor. 61 degrees Fahrenheit compared to 62 degrees Fahrenheit, and the humidity is 43 degrees Fahrenheit. 43% humidity compared to the humidity sensor at 44%.
And for our engineering analyses, we had three critical analyses that we focused on. Most important of which was our condensation rate, which had multiple sub-analyses that it depended on. And our other two were our energy required for condensing and our design limiting material properties. For our condensation rate analysis, it depended on an input of the airflow rate given by our fan, as well as the ambient air temperature of the surroundings. And that allowed those two inputs would allow us to calculate the amount of water that we condense in a 24-hour period. And these are the results that we got from this, which are theoretical calculated amount of condensed water would be 1.43 liters, whereas our actual condensed amount was, as Kirsten said, 0.118 liters. That was 8.25% of our target, and that difference is due to inefficiencies in our system. For our condensation energy analysis, there are two sources of energy consumption. Those are the fan and the cooling plate. In order to analyze the energy required to condense water, we calculated that the heat transfer rate out of the air was 282.7 watts. And these other numbers are talking about what power we have to give to the system in order to achieve condensation. It says 90 watts for our power draw for our thermoelectric coolers, but in reality, due to inefficiencies in the thermoelectric coolers, our power, or the amount of heat that we can transfer across that thermoelectric coolers is less than that. And that difference is, that key difference is the reason why we were not able to condense as much water as we hoped. Our total power consumption for the system is 135 watts. This is a setup of what our thermoelectric coolers looks like. We will be revising this in coming next quarter for a more efficient setup. And as for our design limiting properties, we went through the process of trying to determine which material would be best for our condensation plate. We needed it to be able to conduct heat and condense water, or collect water. Therefore, it had to have a surface area, but that's easy to do without choosing a material. It also needed to be food safe and non-corrosive. So narrowing this down, we decided on diamond, copper, silver, aluminum, or cast iron. Then we ranked those based on their cost as well as their ability to transfer heat. And the aluminum came out on top, and so that is what we chose for our plate.
All right, and here's our updated project. I'm excited to talk about this. This is some of the cool updates we'll be starting next quarter and a little bit during winter break. Starting off, block diagram. Here's what we have already done from the RRP. The green box is atmospheric sensor system. Includes John's humidity sensor, temperature sensor, and microcontroller all integrated together as we saw earlier. Those are working great. We're super happy with that, as well as the user interface. Just kind of displays the temperature there. We also have the fan already picked out and working, and that might be something we change if we want to go with a smaller fan or something that's a bit more efficient. And we also have the condensing plate already picked out, and water collection goes into the bucket, obviously. That part's not too difficult. Heat sink is a similar thing, we already have that picked out, ready to go. Things we're going to upgrade, those are in the red boxes. It's kind of a cyclical motion since it's a full system, but I'll start with the power supply, it makes no sense. Power supply, so far we've only used the lab power supply, and that's been working well for us, but as we talked about earlier, we're not being efficient enough. We need to use less power and we need to get more condensation out of it. So we're going to work on optimizing the power supply so that we have minimal power coming out of it, and that's still enough to condense as much water as we need. Part of that will be getting upgraded thermoelectric coolers or upgrading our cooling systems. We'll talk about in the next slide. For now, let's think there's just upgraded thermoelectric coolers. We want to get better ones. Right now, we think we do not have good enough thermoelectric coolers. We saw earlier, Matt mentioned that they're rated at, or they're pulling 90 watts of power, but they're definitely not actually pulling 90 watts of heat out of the air. Even if they were, that wouldn't be enough for our system. So we need to upgrade those, get those working a lot better for us. Part of that will be integrating the current controller. This current controller will be devices linked to the microcontroller. Basically, we'll be trying to run just enough current into the new thermoelectric coolers to get the right temperature to condense water. If we're running too much current, then we're going to be losing a lot of power, which we don't want to be doing over time. So it's kind of all integrated together there. The last part of that will be thermocouple. We'll be using a thermocouple, which John actually already has. We might have to show it somewhere. We'll be doing that, just putting that right on the condensing plate. That'll tell us the temperature of the condensing plate at any given time. And from that, we'll know how much we need to cool it, giving us information for the microcontroller to tell the current controller how much current to give to the upgraded thermoelectric coolers. And all that together will help us to optimize our power supply. And this is our winter break of the first week schedule. Over winter break, we are going to keep on working. We don't want to lose those 3 weeks. I'm going to start off by analyzing other potential methods of cooling. That includes looking into the upgraded thermoelectric coolers and picking those out. As we also say down here, we want to order more of those. So maybe even order some of the current ones we have and test out different methods for those, such as stacking. That may be one of the methods we go with. We just learned that recently that stacking Peltier devices can possibly increase how much heat you're pulling out of the air. We also look into doing a closed loop refrigerant cycle. We kind of denied this idea earlier on because it wouldn't make sense to be sending in refrigerant, but we want to go back and revisit that just in case sending in a little bit of refrigerant would produce a lot of water. It would be very fitted for us to do that. John will be working on programming the thermocouple sensor and increasing the precision of our current sensors. Just kind of making final tweaks to our atmospheric sensor system, getting perfect, ready to go. That way, in the winter quarter, we are able to jump right in and start working on making the system fully autonomous.
Yeah, and so starting off winter quarter strong, we're planning on starting off with performing cost reduction analysis. So something that we didn't focus on a ton this quarter is the kind of logistical side of, or the logistical problems that our specific problem faces. Since our project is focused towards relief organizations, the logistics of shipping and the cost of actually putting together our product matters a ton. And so that's something that we're going to focus on a lot more winter quarter is performing cost reduction analysis, and that's actually going to continue on throughout most of the quarter. But specifically, we're going to look into external sourcing for certain components, as well as affordability for or overall affordability for relief organizations. Another thing that we're doing right off the bat come winter quarter is we're going to be building an updated cooling plate. As kind of mentioned before, we're planning on, if we're sticking with Peltier devices, we're planning on having an updated configuration of those devices integrated with our cooling plate. And yeah, so that should be, or we're going to be doing that come the first week. We're also going to make sure that all of our devices are working as efficiently as possible before assembling the entire plate together. So yeah, those are some of the things that we are starting off the quarter with. Are there any questions?